So let's talk about ice cores and ice core data. As I mentioned before, to produce ice we need snow to accumulate for up to, say, 150 meters depth, and then it's heavy enough to compact the snow into ice, and we'll have ice as long as it doesn't melt in the summer. And if we drill into this ice, we can get information about the climate in the past. Here you can see some ice cores which are being drilled, and you can see the scientist holding up one of these ice cores, and all the climate information is within the ice, whether it's about the greenhouse gases, about the temperature of the Earth. And again, the further down we drill into the ice, the further back in time we can go. Now, what can the ice cores give us? So first of all, they give us, and we've already seen this, the information about the trace gases or greenhouse gases. Trace gases, that means that these gases are very small amounts, less than maybe 0.5%, even 0.1% of the air around us in the atmosphere. So there's just a trace of them in the atmosphere. So when you hear about trace gases, we're talking about these very small concentrations of gases, but these are also the greenhouse gases which cause the climate to warm. So we can get information about these trace gases, greenhouse gases in the ice core. And we can also get information about temperature, and this is using chemical analysis based on isotopes, especially oxygen isotopes, but there's also carbon isotopes. I'll talk about that in a minute. I'll explain what an isotope is. And we look at the ratio of these isotopes, these different types of atoms of oxygen which we find in the ice, and it tells us something about how the temperature has changed over time. And basically, we'll come back to this, but the greater the amount of this oxygen 18, the greater the temperature was in the past. Now, again, this method is only useful where we have ice, which remains throughout the summer and builds up over time. And so there are only really two places, in Greenland and Antarctica, where we can use this. There are a few other smaller locations, but really there are only two locations where we can use ice cores to study the climate, unlike tree rings, which we can go to many other places. And the length can go from 10,000 to 800,000 years. We've already shown that you can get information about greenhouse gases for 800,000 years back in time. We can also get information about temperature. So a lot of information we can get from the ice cores, even about volcanic eruptions, and because we can look at the actual acidity of the water or the snow which is falling on the ice. So let's again talk about these bubbles. Here we can again see in the bottom a slice of ice from one of these ice cores, with the little white dots are the actual bubbles of air inside the ice core. On the top we have a image which is in polarized light, so we can see these different colors, but the little gray bubbles, you can see gray, black, circular bubbles. These are the bubbles of air inside the ice core, which we can then open very carefully and measure what the concentrations are in these bubbles at every level down in the ice core as we go back in time. And we've already seen this, but here we have then 2,000 years of data from Antarctica, which is showing in the different colors the carbon dioxide, the methane, the nitrous oxide, which are more or less constant in the ice cores for nearly 2,000 years. And then again, around about the 1800s, we started to burn fossil fuels, started to farm for the whole villages, and all this resulted in the increase in these greenhouse gases in the atmosphere, which continue today. So let's talk about these isotopes that we can use for measuring the temperature back in time. When we look at the oxygen in the room around us here, most of the oxygen is what we call oxygen 16. In the oxygen atom, we have 8 electrons. You can see this cloud of electrons around the center, the nucleus of the atom. And we have 8 protons and 8 neutrons. 8 plus 8 gives us 16. We call this oxygen 16. And that's the majority of the oxygen in the atmosphere. There's a very small fraction of the oxygen, about 1 out of every 1,000 atoms, that has 2 extra neutrons. And so we have 8 protons, 10 neutrons, and therefore we call this oxygen 18. Oxygen 18, because it's got 2 extra neutrons, is actually heavier, so we also call this the heavier isotope. And oxygen 16 is the lighter isotope. Now, if we want to measure the temperature or monitor the temperature, we can look at this ratio, and what happens is that, again, when we have evaporation from the oceans, if the temperature changes, the lighter isotope will leave first. So oxygen-16 is going to leave the oceans more readily than oxygen-18. And so here already, as the temperature changes, we have a differentiation when we're looking at the ratio of how much oxygen-16 and 18 we have in the ocean water and how much we have in the atmosphere. This is going to be affected by the temperature of the oceans. And we find that in warmer periods, we generally have more oxygen-18 in the water compared with colder periods. So if we track, for example, in coral reefs, which are basically reacting to the water, the amount of oxygen-18 and 16 in the water, we'll see changes both in the coral reefs, in the amount of oxygen which relates to the temperature of the water. But also, if we look in the snow, which falls over Antarctica, we'll see changes in the ratio. But something else happens once the oxygen, the water and the oxygen go into the atmosphere due to evaporation. We have transport going to the high latitudes, which eventually falls as snow in Antarctica or in Greenland. And along the way, the heavier isotope again will fall out quicker in rainfall. And therefore, as we go further and further to the north, we start to deplete this ratio and we get less and less of the oxygen-18. And in fact, by the time we get to the snowfall of Antarctica, we see that we actually have about 5% less oxygen-18 than we see in the ocean waters at the same time. So when we look at this ratio, again, we can see both the change in the temperature in the ocean, but also we can see changes in the ice, which tell us something about the relative change in temperature which occurred in the past. We don't know exactly what the temperature was, but comparing it to today's temperature, we can see the ups and downs of the temperature by looking at this ratio in the ice cores. And we can also look today and make a graph here where every point is a sample taken, say, from Antarctica, from the snow today, or the ice in Greenland and Antarctica, and we can actually see the link between, say, the temperature at the time of the sample and the actual amount or the depletion of this oxygen-18 in the snow or in the ice. And what we see for that colder temperatures, we have a lower increased depletion. This is a 0 going down from 0 to -6 on the scale. And so the more depleted in percentage, 5% less, 6% less, the colder the temperatures. And so we can measure these isotopes in the ice and convert that to temperature changes of the climate. So now we can go back again to what we saw before, again, 800,000 years at the top of carbon dioxide and at the bottom temperature, but temperature measured with these isotopes. So it's a relative change. Again, today is 0, so we're living on 0 on this graph and going back 800,000 years. So we see that the temperature today is around about 0 degrees. That's not 0 degrees, that's our reference plane. And when we go back to the last ice age, it was maybe in Antarctica, this is temperatures for Antarctica, were about 7, 8, 9 degrees cooler than today. On a global scale, it was about 3 or 4 degrees cooler, but in Antarctica, we see it even colder. And we see this agreement, the ups and downs of carbon dioxide in the top and the ups and downs of temperature down below. And again, as I mentioned before, when we had periods of high concentrations of CO2, like over here, we also had high temperatures. And when we had the minimum amount of CO2, we had the coolest temperatures, what define the ice ages. And we'll talk a little bit more about why we have these ups and downs, these periodicities in some of the future units. And what's happening today, put that in context of what we see today. Again, 800,000 years of carbon dioxide in temperature. And just in the last 200 years, we see this is basically a straight line going straight up to today, where today the carbon dioxide is already close to 420 ppm. And again, the question some people raise is, why hasn't the temperature gone up more than we see at the moment? Why haven't we seen a fever of more than 1 degree? But we can see a very nice match between the peaks of the temperature, the peaks of the greenhouse gases, the minimum of the greenhouse gases, and the temperatures. And this is all coming from the ice cores and the data we can get out of the ice cores. Based on that and the vegetation, we can also reconstruct the extent of the ice sheets in the last ice age. So this is a view looking from the North Pole. On the right, we can see the present climate, where basically Greenland is the only one which is covered in ice sheets, as well as the sea ice, which is over the North Pole. But if we look at what happened 18,000 years ago, we have Greenland, but also we have the whole of the northern part of Europe, Scandinavia, the whole of Canada, down to the Great Lakes, all covered in ice. And again, we can see that in the region of Russia and Alaska, this was above sea level. Homo sapiens could walk across from Asia into North America because the sea level went down 100 meters. Today, there's ocean there and people can't walk across there. So we can use all of these methods that I've shown, the pollen from deposits, the ice cores, tree rings, to reconstruct what the climate looked like 18,000 years ago, 100,000 years, even 800,000 years ago.